Greetings, A-level chemists. So everybody loves a KP question, and we're not talking about nuts here, but we are talking about the equilibrium constant for pressure. So what's happening is we've got the Haber process where atmospheric nitrogen is combined with hydrogen, and we force it to make ammonia, which is a good precursor to fertilizers and is a reaction that feeds the world. Okay. So we're given lots of info. Before I even start looking at the text and decoding it, what I want to do is get my reaction down. So N2 plus 3H2 makes 2 lots of NH3, okay? And then I'm going to set up a little table, and I've already done it in the interest of time, but you might know this table. We've got the initial, change, and the equilibrium, so this is called an ICE table. For KP, you need 2 extra row headings, and one is for the mole fraction, chi, and one is for the partial pressure, P. Okay, then I start looking at the text, and then I have a look and think how much of my reactants were mixed initially. And normally that information is found in the text, and I've circled it. So it's 0.46 and 0.46. I've got 0 moles of NH3 produced initially, okay, because it hasn't started yet. And then I look at the change, and this is all to do with the stoichiometry. That's all we're doing. We're looking at the stoichiometry. So if X moles of this react, because there is an imaginary 1 here, look at the ratio in which these guys react. It's 1 to 3. So if X moles of this reacts, that means 3 lots of X are going to react with respect to the H2. Okay, well, how many moles of NH3 are going to be produced? I guess that's the next question. Well, let's look at the stoichiometry. So there is a 2 in front of the NH3, so we're going to form, hence the plus, 2 lots of X. Okay, that's our change. I like doing it in terms of X. It's helpful for me. If it's not helpful, you can just get rid of the change column, or row, I should say. So then we should be given some extra information about how many moles of one species we have at equilibrium. So when it reaches equilibrium, we've got nitrogen gas and we've got 0.42 moles. So first thing is to find nitrogen gas. It's here. And at equilibrium, the number of moles is 0.42. Sorry, I have to keep that consistent and put that black because it's just glaring red there. Okay, so how do we read this? How to read this first column? So it actually reads as an equation. So 0.46 minus X equals 0.42. So we can use this to calculate what X is. So X equals 0.04 moles. Okay, so that's what my X is. So that's how we read that. Same thing here. We read the second one as, for H2, 0.46 minus 3X. And what does that equal? Well, now that we know what X is, we're going to times it by 3 to get that value, right? So 0.46 minus 3 times 0.04, and that equals that value. So this is 0.46 minus 0.12, and we should get a value of 0.34. Cool. Hopefully that makes sense. Okay, and then we'll do the same for the last one. So we're reading this as 0 plus 2x equals what? Well, we know that x is 0.04. So 2x is equal to 0.08. So this is equal to 0.08. Okay, so then we have a look at the fraction of moles, and it is literally the fraction of moles. So one number of moles for the reactant divided by the total number of moles in the vessel. So we have to work out what N total is, and to work out what N total is, all we do is add up the number of moles at equilibrium. So these bits in red. So we're just going to add all of these up, and that's going to give us the total number of moles at equilibrium. So 0.42 plus 0.34 plus 0.08, and all of this equals 0.84 mole. Now, if I want to work out what the fraction of moles is for nitrogen, that is going to be the number of moles of nitrogen at equilibrium over the total number of moles, which is 0.84. And then remember that the moles cancel out because it's a fraction. So this is just a number. So this is equal to 0.5, no units. Okay, so that's how we do it. So this is 0.5. And then what we do is we just go through that same process for each species in the reaction. So 0.34 over 0.84. I'm not going to put the values in just yet. I'm just going to leave it like that. I'll let you guys do that if you want. And then 0.08 over 0.84. I'm actually going to leave that as a fraction for now. So then, using my N2 as an example, to work out what the partial pressure is, that's the mole fraction of N2 multiplied by P total. So where do I find P total? Usually in the question. And a tip here, don't change any units. If it's kilopascals, leave it in kilopascals. So what is my mole fraction of nitrogen? It's 0.5, and my total pressure is 500 kilopascals. So this has a value of 250 kilopascals. So done. Okay, so just going to rub that out to give us more space for the actual calc. So why didn't I put numbers there? I'll tell you why. Because what I can do, I would leave everything in my calculator and round up towards the end, okay? So if we times that by 500, what do we get? And we'll do the same thing here. So 0.08 over 0.84 times by 500, and we can round up at the end. Okay, so what do these work out as? So we should get 202.38, and that's in kilopascals, and we should get 47.62 also in kilopascals. Okay, we've actually done all the prep and all the hard work, so now it's just a process of plonking these numbers into our expression for Kp, which we need, and then processing it in our calculator. So Kp is the partial pressure of NH3 squared. So you can use curly brackets here, parentheses, but you're not allowed to use square brackets because that refers to concentration. This is looking at pressure. So the species are in the gas phase. Okay. And the partial pressure of N2 times the partial pressure of H2 raised to the power of 3. So once I've done that, you've got all these values, stick the values in. So this is for ammonia. And just make sure you get the order right rather than doing it upside down. Okay, so take your time. So this is going to be 47.62 kPa all over 250 kPa multiplied by okay, by the way, that should be squared. I'm just going to leave the units out actually for a second to make my life easier. All right. And then, so my hydrogen value is 202. And that is cubed. Okay, so now that we've got everything into our expression with Kp, put this into your calculator and you should get a value of Kp as 1.09 times 10 to the minus 6. Okay, initially I started putting my units in, but actually it made it more messy, so we can do our units after. So we need to state our units. So we have kPa squared for our numerator, and then for our denominator, for N2 we have kPa to the 1, and then we have kPa to the 3. So when the base is the same, what do we do to the index? We add it together. So this will reduce to kPa 1 plus 3. 1 plus 3 equals 4. Okay, so when the base is the same, what do we do when to the index when we're dividing? This becomes kPa 2 take away 4. So 2 take away 4 is minus 2. So my units are kPa to the minus 2. Okay, and there you have it. And there is your answer. It's way less than 1, so the position of equilibrium is way over to the left-hand side as well. Okay, thank you for watching. Ta-ta.